Welcome to Next Gen Manufacturing. Today, we're going to dive into a pretty remarkable material that is, believe it or not, quietly building our future, from those giant wind turbines powering our cities to the high-performance cars we all dream of driving.
You know, this is the fundamental question that engineers grapple with every single day. Doesn't matter if it's aerospace or renewable energy or even just basic infrastructure. The goal is always to push the limits. But to do that, you absolutely need materials that can keep up with those ambitions.
For the longest time, we've had to rely on the classics. Steel? Yeah, it's strong, but man, it's heavy and it rusts. Standard plastics are nice and light, but they often just don't have the strength or the durability we need. And then there's aluminum, which is great, but it can get pretty pricey and takes a ton of energy to make. All these limitations created this gap in the market and a real hunger for something better. And that is where our hero material comes in. It's not just one thing, it's a whole class of materials engineered specifically to fill that gap. Think of it as a true super hybrid that combines the best properties of everything else, but without all the drawbacks.
Okay, so what is this stuff?
It's called Vinyl Ester Resin. At its heart, it's a high-performance material that just sits in this perfect sweet spot. It's kind of like a chemical cousin to both polyesters and epoxies. In fact, some people are even starting to call them epoxy vinyl esters now, just to really drive home how close they are to that super high-strength epoxy family.
So this brings us to a classic dilemma that engineers have faced for decades. On one side, you've got your polyester resins. They're affordable, pretty easy to work with. On the other side, you have epoxy resins. They're the gold standard for strength, toughness, and fighting off chemicals. For a long time, you had to pick a side, save money, or go for ultimate performance.
And this is the absolute magic of vinyl esters. They give you the easy processing and cost-effectiveness of a polyester, but with performance that gets right up there with high-end epoxies. You literally get the best of both worlds in a single material. That old engineering problem? Solved.
But here's the really cool part. This isn't some one-size-fits-all solution. One of the most powerful things about vinyl ester is that you can basically custom design it at the molecular level. You can literally create the perfect resin for almost any specific job you can think of. The basic recipe is actually pretty straightforward. First, you start with a really strong, stable epoxy molecule. That's what they call the backbone. Then, you add a reactive acid to it. And finally, you dissolve that whole new molecule in a liquid monomer, something like styrene. That liquid is what makes it easy to work with before it all hardens into the final, super strong solid. Now, just by tweaking one of those ingredients, you get a totally different material. The most common flavor is the bisphenol A type. This is the industrial workhorse, right? The go-to for just countless jobs, because it hits that perfect sweet spot between performance and price. But what if you need something way tougher? Well, you just swap out that standard epoxy backbone for one called Novolac. That simple change creates a much denser molecular structure, and the result is a resin with just phenomenal resistance to really high temperatures and nasty chemicals. Need it to be fire-safe? No problem at all. Chemists can literally build bromine atoms right into that epoxy backbone. This creates what's called a halogenated vinyl ester, and it has these incredible fire-retardant properties. It's actually self-extinguishing. How cool is that? And for jobs where you need to withstand heavy impacts without shattering, you got it. You can mix in elastomers, which are basically rubber-like molecules. This gives you a flexible version with fantastic toughness and the ability to bond like crazy to other materials. Okay, so we know what they are and how they're made, but why are they so ridiculously tough? Well, the secret, it's all in their unique molecular architecture.
Right, here's the secret sauce. See, with other resins, chemical links form all up and down the molecule, but with vinyl esters, they only react at the very ends. This means that whole long central part of the molecule stays free and flexible. It can actually stretch and move, which lets the material absorb impacts and stress without cracking. It's what makes it tough, not brittle.
So just how tough are we talking? Let's put a number on it. That high-performance Novolac version we talked about? It can handle temperatures up to 190 degrees Celsius, that's a blistering 374 Fahrenheit, before it even starts to deform under load. That is some serious heat resistance.
And this strength isn't just about heat. Check out how it handles chemical attacks. You throw something as corrosive as 37% hydrochloric acid at a standard polyester, and it's going to fail pretty fast. The standard vinyl ester, it holds up really well, but that specialized Novolac version, it can handle that same nasty acid at temperatures over 80 degrees Celsius. Just incredible.
So what's the secret formula for all this durability? It really boils down to three things: First, vinyl esters just have way fewer of those weak spots that chemicals love to attack. Second, all the reactive parts are safely tucked away at the ends of the molecule. And third, those stable ring structures in the backbone, they act like a tiny chemical shield, protecting the core of the material. Brilliant stuff.
Okay, so all this amazing science is great, but it translates directly into real-world, next-gen manufacturing. This is not some lab curiosity, folks. This stuff is already out there, building the world all around us right now.
Let's start with renewable energy. The blades on modern wind turbines are absolutely massive, and they have to endure unbelievable stress for decades. Vinyl ester composites are perfect for this job, giving them the strength, the lightness, and the fatigue resistance they need to harness the wind. In transportation, this stuff is everywhere. It's used to build strong, lightweight boat hulls that just laugh at saltwater corrosion. It's in high-performance car parts, and it's used to line the inside of chemical tankers so we can safely move materials that would literally eat right through steel.
And it's so critical for protecting our industrial infrastructure. Just picture the inside of a factory chimney or a chemical pipe. They're lined with vinyl ester composites to shield them from a constant barrage of hot, corrosive gases and liquids. It keeps things safe and makes the equipment last for years longer.
And the list just keeps on going. It's used in aerospace components for high-pressure gas cylinders, gigantic chemical storage tanks to make concrete and mortar stronger, and even for building really durable, long-lasting swimming pools. The versatility is just off the charts.
Which really leaves us with a pretty fascinating question, doesn't it? We now have a material that we can customize to conquer extreme heat, to resist fire, and to stand up to the most corrosive chemicals you can imagine. The only real limit, at this point, is our own imagination. So what are we going to build with it next?